Welcome back, everyone, to the online Graphs and Matroids seminar. Today, we're happy to have Tung Nguyen from Princeton. So whenever you're ready.
Yeah, thanks, Jack. Thanks for the invitation and the introduction to speak here. So what I'm going to talk about today will not be about Matroids. So I apologize for that. It's only about graphs, right? So only half of the title of the seminar. Yeah, so I would like to talk about some results on the problem of Erdős and Hajnal that just came out a couple of weeks ago. And this is all joint work with Alex Scott from Oxford and my advisor, Paul Seymour. Okay. Yeah, but before going into the details, let me start with some basics, some preliminaries to make sure we are on the same page. So again, for a graph G, I will use standard notations for the number of vertices in the stability or independence number and the clique number of G. Okay. So we all know from basics of Ramsey theory that every graph G will contain a clique or a stable set of size at least some constant times log of the number of its vertices. And I think Erdős and Zacharias in 1935 showed that this constant can be chosen to be 1/2. And a couple of months ago, this was pushed a little bit to 1/2 plus some epsilon. Right. And also, basics from random graph theory shows that this bound is asymptotically optimal for almost every G. In the sense that if you take a random graph on n vertices and with H probability 1/2, then almost surely the random graph will contain no clique or stable set of size bigger than 2 log G. And so this bound is asymptotically optimal. And the problem of Erdős and Hajnal actually concerns the situation where we are excluding a single induced subgraph in G. So an induced subgraph an induced subgraph of G is the graph obtained by removing vertices of G only. So in this talk, I will only talk about induced subgraphs. Okay. And let me say G is H-free for a graph H if it contains no induced copy of H. Okay. And the first observation is again from basic Ramsey theory that if G contains no complete graph on T vertices, then it will contain a clique or stable set of size at least G to the 1 over T minus 1. Yep. And if G is K1T free, if it contains no star with a vertex of degree T, then you can show that you can find a clique or stable set in G of size at least G to the 1 over T. And to do so, you can just observe that the mass degree of G will be bounded by omega of T to the T minus 1, I think. Right. If G is P4 free, then it is well known. G is P4 free means it is a co-graph. And you have many ways to show that G will always contain a clique or stable set of size at least root of the number of vertices. And if G is C4 free, then I think Erdős and Hajnal were the first to show that G will always contain a clique or stable set of size at least G to the 1/3. And I think it is still open whether this 1/3 exponent is optimal. Okay. Yeah, but going back to the problem of Erdős and Hajnal, in 1977, they posed the conjecture that not only in these special cases, if you exclude any given graph H as an induced subgraph, then you will see a clique or a stable set in G of size at least some polynomial in the number of vertices of G. So this will be significantly better than the logarithmic bound that you would see in general graphs. Okay. Any questions so far? Yeah, good. Right. So let me say H has the Erdős-Hajnal property if it satisfies the conjecture. So for example, the last slide shows that KT, K1T, P4, and C4 have the property. And we have a fundamental result of Alan Park and Solimushi from 2001 that says the class of graphs with the Erdős property is closed under substitutions. So what do we mean by substitutions? So let me say I have two graphs, H1 and H2, with the property, and I have a vertex V in H1. And this green rectangle is the neighborhood of V in H1. So by substituting H2 into V, I mean by removing V from H1 first, and then I add a copy of H2 to the resulting graph. And then I make everybody in H2 adjacent to everybody in this green rectangle. And the resulting graph is obtained by substituting H2 into V. And if H2 and H1 have the property, then the Allen-Park-Solimushi theorem says the graph on the right-hand side also has a property. And so this conjecture reduces, this theorem, this theorem of Allen-Park and Solimushi reduces the Erdős conjecture to verifying the Erdős property of prime graphs. Here, H is prime if it cannot be obtained by substitutions from smaller graphs. Okay. So most of the most of the progress on Erdős so far during the last 3 decades has been devoted to proving the Erdős property of prime graphs. So what's known about prime graphs and Erdős? Until last month, all of the prime graphs H known with the Erdős property were the 4 vertex path P4, as I have said, the bull, this configuration on 5 vertices, and this was shown by Chudnovsky and Safra in 2008, and the 5-cycle C5, which was just published this year by the Choir, Chudnovsky, Scott, Seymour, and Spurkle. And this leaves the smallest open case for Erdős, which is the 5 vertex path P5. So what about this graph? A couple of months ago, Pablo Blanco and Matija Bucic proved that every graph G with no induced copy of P5 will contain a click cross stable set of size at least 2 to the C times log G to the 2/3 for some constant C depending on P5 only. Okay. And a couple of days ago, we managed to push this a little bit further. So instead of the exponent 2/3, we push this a little bit to 1 minus liter of 1, where liter of 1 tends to 0 as the size of G tends to infinity. Yeah, but I'm not going to talk about P5 today. Today, I would like to announce a new result with Paul and Alex. It just came out a few weeks ago that there are infinitely many prime graphs H with the Erdős property. And in order to do so, I will first define a family, let me say fancy H of graphs with the Erdős property such that this family contains infinitely many prime graphs. Okay, and so this theorem will follow. So the family is constructed as follows. It contains all graphs on at most 2 vertices, is preserved under taking induced graphs, complements, and substitutions. So this condition is just trivial from what we have already known about Erdős. Okay. And the second condition is more important. So whenever you see a graph in H, in fancy H in the family on at least 2 vertices, and a vertex V that is adjacent to all but except 1 vertex, then the family also contains the graph obtained from H by adding a pendant H to V. So here's the picture. You start with the graph H in the family with a vertex V adjacent to all except this vertex U. And so this green rectangle is the rest of the graph, excluding U and V. Now to create a new graph, you're gonna add a vertex W to it, and then you make W adjacent to V only. And the graph on the right-hand side is in the family. So that's the construction. Any questions so far? Yeah, good. So here are some small examples of this construction of this family. So the 4 vertex path P4 is in the family. And to observe this, you can start with the 3 vertex path P3. This 3 vertex path is in the family because it can be constructed by substitutions. And this vertex, the right-hand vertex, the right-hand leaf of P3 is adjacent to O, but except the left-hand leaf in the graph. And so now you can add a new vertex adjacent to this right-hand leaf only, and then you will get P4. The bull is in the family. Again, you can start with this 4 vertex graph on the left-hand side, excluding the rightmost vertex. And again, this 4 vertex graph is not prime, and you have the right-hand vertex of a triangle is adjacent to everyone except the leftmost leaf. And so you can add a new vertex adjacent to this right-hand vertex to get the bull. And by doing the same thing, you can get this funny-looking graph on 6 vertices, and also this graph on 7 vertices. So these are some small examples. Right, and actually, if you look at this operation a little bit, if you just think about it a little bit, then you will see that actually it contains a prime graph of any order of any size. So for every integer n at least 4, the family contains a prime graph on n vertices. And so now our theorem says every graph in the family has the Erdős-Hajnal property. Right. And this is an even more complicated example. It's just for fun. I mean, okay. So let me observe that. So even though the family contains infinitely many graphs that are not self-complementary, every graph in the family actually has a common property. I mean, prime graphs. I mean, the prime graphs in the family have a common property. And this property says every prime graph H, for every prime graph H in the family, both H and its complement have a vertex of degree 1. Okay, and this is actually not hard to show. You can do it by induction. And so this motivates the definition of another family, let me say fancy J, which is a bit simpler. So, this family is defined as the family is such that every inducible graph for every J in this family, every inducible graph of J either is not prime or contains a vertex of degree at most 1. And you can show that a graph H is in the family fancy H if and only if both H and its complement are in the family fancy J. Again, this can be shown quite simply by induction. And so since most of the papers in the literature concerning Erdős-Hajnal have been about excluding pairs of graphs, we also follow this path by showing that for all graphs H and J in the family fancy J, the pair H and J complement has the Erdős-Hajnal property. Here, this means if you exclude both H and J complement, then you will see a click cross stable set of polynomial size. Okay. And so in particular, as you can see, the family fancy J contains all 4s. And so from this theorem, you can deduce that the pair H and J complement has the Erdős property for all four rests H and J. And I think this was proved a couple of years ago by Chudnovsky, Scott, Seymour, and Sperkel. Yeah, but I would like to put our theorem in a broader perspective. And so this is not only about Erdős, but about something else. And so in order to do so, I will reintroduce the theorems of Erdős and Nikiforov. So some definitions for a graph G and a vertex subset S of G. Let me denote by GS and GS the subgraph of G induced on S. Okay, and let me say the vertex subset S is epsilon restricted in G for epsilon from 0 to 1. If S induces in G or its complement a subgraph with mass degree at most epsilon times S. So the theorem of Erdős, which has been a very fundamental tool, very valuable tool in the investigation of Erdős in the last 10 or 15 years, says that for every graph H and every epsilon from 0 to 1/2, you can always find some delta depending on H and epsilon, such that for every H-free graph G, you can always find an epsilon restricted vertex subset in G of size at least delta times G. And this was proved by Erdős in 1987. And Nikiforov in 2006 went one step further and showed that the condition H-free is actually not necessary. And in fact, to get this conclusion, we only needed that the number of induced copies of H in G is not too many. So for a graph H, and again, for every epsilon from 0 to 1/2, you can find some delta such that if the number of induced copies of H in G is at most this quantity, then you can find an epsilon restricted vertex subset in G of size at least delta times G. And here IND of HG, maybe I should say int sub H of G, denotes the number of induced copies of H in G. So these two theorems are very nice applications of the regularity lemma. And actually, when Erdős first proved it in 1987, it was one of the first applications in graph theory of the regularity lemma. And as a result, the regularity proofs gave tower type dependence of delta on epsilon. And this was certainly very bad. Okay. So for the rest of the talk, I will focus on the quantitative dependence of delta on epsilon for fixed H. Fox and Sudakov in 2008, so 15 years ago, found a way to get around the regularity lemma, and they proved a much better quantitative version of Nikiforov's theorem. They proved that in Nikiforov's theorem, in the counting version, you can actually take delta to be some super polynomial function of epsilon. More precisely, this was 2 to the minus d times log of epsilon inverse square, where d is some constant depending on H only. And again, you get the same conclusion. And if you think about it a little bit, then you will realize that this implies the bound 2 to the c times log G, which was proved originally by Erdős and Hajnal from 1977 as a partial result toward their conjecture. And you can do this by taking epsilon to be to the minus root of 1 over 2d times log G. I won't do the calculation here. So what about the state of the art of the dependence of the quantitative dependence of delta on epsilon? Well, a couple of months ago, we so together with Mattia and Paul and Alex, we proved that we can put a double log function of epsilon inverse in the denominator in the exponent. And again, this gives an improvement on the general bound of Erdős and Hajnal. So this is also the state-of-the-art bound for quantitative dependence of delta and epsilon on Erdős theorem, and also it gives the best known bound on Erdős Hajnal. Okay. Any questions so far? Right. So let me now introduce a property which we call the viral. But before that, let me talk about some conjectures related to Erdős and Nikiforov's theorem. So again, as you have seen from the previous slides, I mean, as long as you can improve the quantitative dependence of delta and epsilon on Erdős and Nikiforov's theorems, you automatically get a new general bound on the conjecture of Erdős and Hajnal. And Fox and Sudakov in the same paper from 2008 actually conjectured that delta in Erdős theorem can always be chosen to be a polynomial in epsilon. And formally, for every h, you can find some d such that for every epsilon from 0 to 1/2, and for every h-free graph G, there is an epsilon restricted vertex subset in G of size at least epsilon to the d times G. And let me say H has the polynomial Erdős property if it satisfies this conjecture. So one thing to note here is if you don't believe Erdős Hajnal, then there is no reason to believe the conjecture of Fox and Sudakov, because as you can see, it implies Erdős Hajnal. And but since we still don't know much about Erdős Hajnal, we decided to go one step further and conjecture that this polynomial phenomenon in Erdős theorem can actually be extended to Nikiforov's theorem. And we conjecture that, in fact, delta in Nikiforov's theorem, the counting version, can also be chosen to be polynomial in epsilon. And so now I can introduce the viral property. I can define the property now. Let me say the graph H is viral if it satisfies this second conjecture. Okay. And again, the viral property implies the polyviral property. And let me remark here that the viral property is a very strong quasi-randomness property, because here, the condition about counting into subgraph means that the graph G is quite close to random. Okay. So let me recap 3 levels. The weakest level that I introduced so far is the Erdős Hajnal property that H has the Erdős Hajnal property if excluding H, and then you get a click-cross stable set of polynomial size. The second level is the polyviral property, and the strongest level is the viral property. So we know polyviral implies Erdős Hajnal and viral implies polynomial Erdős. And so far, I have never seen any proof that shows Erdős Hajnal implies polyviral or polyviral implies viral. Okay. So I would like to remark here is, as you jump from Erdős Hajnal to polyviral, the host graph G becomes less relevant, in the sense that the density parameter, the restriction parameter epsilon, will be more important. And if you jump from polyviral to viral, then that means the condition H-free is less relevant. And to think about the relative strength of these 3 properties, I would like to encourage you to think about the case of the 4-vertex path before. So we all know it is trivial that before has the Erdős Hajnal property. And I think it is a pretty nice exercise to try to prove that P4 has the polylateral property. I mean, it will help us understand a little bit more about co-graphs. But I have never seen any super straightforward proof for the fact that P4 is viral. So, I mean, there might be an easy proof, but I don't know. So maybe P4 is a good way to think about the relative strength of these three properties. Okay, so since now we have seen these properties, it might be natural to try to extend what we have already known about Erdős to these properties, the polylateral property and the viral property. So let me remind you the fact that the graphs with the Erdős property are preserved under substitutions. And this is the theorem of Allenpak and Solimoschi. And similarly, we can show that the class of viral graphs is closed under substitutions. So this is a bit funny because I don't know if we can do the same thing for the class of graphs with the polylateral property. And here we can explain that this phenomenon by the fact that the proofs of Allenpak Solimoschi was based on a counting scheme. And that counting scheme works equally well in the case of viral graphs. And with Paul and Alex, we managed to prove that all graphs known to have the Erdős property are also viral. So these results may suggest that perhaps graphs with the viral property are the right concept to investigate. We hope. Yep. Any questions so far? Right. So since I was talking about isocline pairs of graphs and Erdős, I think it might be wise to try to extend the viral property to finite families of graphs. So let me say a finite family fancy F of graphs is viral if you can find some D, such that for every epsilon from 0 to 1/2 and every graph G with not too many induced copies of every graph H in the family, you can always find an epsilon restricted vertex subset in G of size and of measure at least epsilon to the D. And then again, so we have a fact, which is a little bit vague, but I mean, as long as you know the proofs of the similar statement of the viral property for single graphs, you can extend it to finite families of graphs. So the finite families with the viral property are closed under taking induced subgraphs, complements, and substitutions. Okay. And so again, let me go back to the family fancy J, which is the family of the graphs J, such that every induced graph of J is, either is not prime or contains a vertex of degree at most 1. And and our theorem was, the pair H and complement J has the Erdős property for every H and J in the family fancy J. And what we actually showed was the pair H and J complement is viral. And this is actually the main result. Yeah. Okay, so before I go into the idea of the proof, let me introduce a couple more definitions. So I have a graph G and two sets A and B. And let me say, and also a real number X positive. And let me say B is X sparse to A if every vertex in B has at most X times A neighbors in A. So B is X sparse in A if every one in B sees at most an X fraction of vertices in A. And similarly, B is X dense to A if everyone in B unsees at most an X fraction of A. Okay. And blockades are just sequences we want to be N of disjoint subsets of G. And the blockade is X sparse if every block on the right-hand side is x bars to every block on the left-hand side, and similarly for x dense. And then I say the length of the blockade is the number of blocks that it has, and in this case, this is n, and the width of the blockade is the minimum of the size of every block in the sequence. Okay. And to prove the viral property, we try to make some, more definition. I mean, more definition that can allow us to deduce the viral property easier. And this is the divisive property. And let me say, if a family fancy F has the divisive property, if there are numbers B and C positive, so here B is very large and C is very small, such that for every x from 0 to C and every graph G, again, with not too many induced copies of every graph H in the family, you can always find some K between 2 and 1 over X, and then X sparse or X dense blockade of good length and good width. Sorry. So here, by good length, I mean of length at least K, and by good width, I mean of width at least G divided by K to the B. So here the length and the width are polynomially related, and the condition K from 2 to 1 over X is important, especially the upper bound 1 over X on K. And if you're familiar with recent progress on Erdős Hajnal, you will see that this definition is actually an extension of the so-called quasi-Erdős Hajnal property that was used for progress on string graphs, on ordered graphs, and on C5. And as those papers has shown, the quasi-Erdős Hajnal property is equivalent to the Erdős Hajnal property. Quasi-Erdős Hajnal property means you can find a complete or incomplete blockade of any length, and again, of width polynomially related to the length. And similar to this situation, we have that the finite family F is divisive if and only if it is viral. Okay. And in order to show that H and complement J is viral, we prove that this pair is divisive. Okay. Any questions so far? Okay, so now let me go to the into some ideas of the proof of the theorem. I would like to call this idea density decrement. So in contrast to the familiar density increment that you often see in extremal graph theory. Okay. So again, let me state the goal is we want to find some small c and some large b, such that for every x from 0 to c, and if the number of induced, I mean, if the measure of the copies of H in G is most x to the b times H, and again the same thing for complement of J, and G contains an x sparse or x dense blockade of length at least K and width at least G to the K, G divided by K to the B for some K from 2 to 1 over X. Okay. So an observation here is we're done. I mean, we can achieve this goal if we can find an x square restricted subset, vertex subset Z in G of measure at least some fixed polynomial in X. Why? Because then we can just take K to be 1 over X, we can take B to be sufficiently large, and we can partition Z arbitrarily, I mean, equipartition Z arbitrarily into 1 over X subsets of size roughly X times Z. Okay. And this is actually how you prove that the viral property implies the divisive property. So we're done if we can get such a set Z. But this sounds a little bit contradictory at first because we're trying to prove the divisive property, and such a set Z would already gives you the viral property of the pair H and J complement. But we can make it work as follows. So as a first step, we follow the well-trodden path from the previous papers. We fix some small c positive, and we try to apply Nikiforov's theorem to get some c prime positive, very small, such that again, if G contains few induced copies of H and J complement, then we can always find a C square restricted vertex subset in G of size at least C prime times G. And so here's C square, and so I chose C square in order to make it consistent with X square. Okay. And so here C and C prime are just constants depending on H and J. And so I can arrange B so that B is at least some D, where D satisfies C to the D is small, some C prime is smaller than C prime. And so I'll have X to the B is less than C to the B and less than C prime. And so I can always get such a restricted subset S in G, given the initial condition in the first item, in the first bullet. Okay. Great. So now let me say again, there is a C square restricted vertex subset in G of size at least C prime times G, and is at least C to the D times G. Okay, so here the idea is, so starting from S, we will try to decrease the restriction parameter starting from C prime, so starting from C square, step by step from C square to X square. And at every step, we shrink the current restricted vertex subset by not too much to get a new restricted vertex subset with better restriction parameter. Okay, and if we can do so, then we can gradually decrease the restriction parameter from C square to X square. And to make this more precise, so now let me try to fix X, and I'm still assuming that X is a very small variable, much smaller than C. And again, I am going to use a floating variable Y between X and C. And I'm going to assume there is an intermediate Y square restricted vertex subset R of S in G of measure at least Y to the D. And so the size of R is going to be at least X to the D times G in particular. Okay. And since we're talking about excluding a graph and the complement of another graph, I can assume that R induces in G a subgraph with mass degree at most Y times R. Okay. And here we note that the density of copies of H and J complement in GR is still at most some fixed polynomial of X. I mean, actually, it is not a fixed polynomial of X. It's actually X to the B minus something. But we will go back to that later. So here, an ideal scenario for us is there is always an X-sparse or X-dense blockade in GR, which has length at least 1 over Y and width at least Y to the B times G. And if that always happens, then we can just take K to be 1 over Y and be happy, right? But if you think about it a little bit, then this did not happen. The reason here is just right at the first step. If you take Y to be C, which is small, and you take X to be 1 over G, for example, and for any fixed B, this would give you the strong Erdős property of H and J complement. You can always find a complete or incomplete pair of linear size in G. But this did not happen always this did not happen always because H and J might not be forest. So this would fail if H and J are the bull, for example. Right. So so we cannot get this always, and this is where the structure of H and J as members of fancy J comes into play. And again, by what we have known about the viral property, we may assume that each of H and J has a vertex of degree exactly 1, because otherwise they are not prime. I mean, one of them is not going to be prime, and you can apply induction. Okay. Right. So in order to make use of the structure of H and J, I'm going to have a standalone lemma. Okay. So now I will only talk about X and Y, and I will assume that H has a vertex V of degree 1. And now I have a graph F with mass degree at most Y square of F. And then the conclusion is one of these 3 outcomes. Either you see lots of copies of H in F, or you can locate a vertex subset Q in F such that Q induces in F a subgraph with few induced copies of H minus V. Or you can find an X-sparse blockade in F of length at least 1 over Y and with at least some polynomial of Y times F. So here I mean that the numbers are not super important. I mean, the point here is the exponents of X and Y are still linear functions of A. Okay, and this holds for any A at least 1. Any questions about this lemma? Okay, so now let me explain how you can apply this lemma to prove the main theorem. So now we would like to apply the lemma with F equals J of R, JR, and then we want to put A to be D squared times the size of H minus V. So here D is now increased a little bit to also verify the viral property of H minus V and J complement. And here we are using induction. Okay. And so we know that J of R contains few induced copies of H. So the first outcome doesn't hold. G of R also doesn't contain any blockade in the X-sparse blockade of length at least Y inverse and of this width. So the third outcome of the lemma doesn't hold. And so the second outcome has to hold. Okay, so that means you can find a subset Q of R such that the number of induced copies of H minus V in GQ is at most this quantity, because I applied the lemma with A chosen to be D squared times H minus V. Okay. So now I'm going to use the viral property of H minus V and J complement. Okay, then I'm going to get a Y to the D restricted vertex subset I Y of Q and of size at least Y to the D square times Q and at least these quantities. So the point here is the new restriction parameter now is going to be at most Y to the D, and the shrinkage factor is going to be at least Y to the D square plus 1, or at least Y to the 2 times D square, let me say. So every step by getting a new vertex subset, I mean, you have bumped up the restriction parameter by a power of D. It's not really bump up, but you have decreased it. Okay, and the shrinkage factor, in some sense, is proportional to the new restriction parameter in some sense. Okay. And so now we can continue this process until the restriction parameter drops below x squared. Okay. And at the end, you will see an x squared restricted vertex subset Z in G with measure at least x to the 4d square altogether raised to the power of some exponential sum, because every step we have raised the restriction parameter to some power. Okay, and the same thing for the shrinkage factor. And so at the end, the measure of Z in G is going to be at least x to the 8d square, say. I mean, the exact numbers could be a little bit different, but they are still basically the same thing. Okay. Yeah, so that's how you can use this standalone lemma together with the density decrement idea to get the full theorem, the main theorem. So now it remains to prove this standalone lemma. But before I go to the lemma, any questions? Okay, so in order to prove the standalone lemma, I will prove standalone lemma prime. So this is like a pre-lemma. So again, I have a vertex V of degree 1 in H with unit neighbor U. Now again, F has mass degree at most YF, so it is not Y squared times F, but it is Y times F. Okay. Then again, I have 3 similar outcomes in this lemma prime. But compared to the previous lemma, the second outcome has changed to the number of induced copies of H minus V in F. And the third lemma, and the third outcome is now changed to you can always find a sparse pair in F of good size, of this size. And in order to deduce this standalone lemma, I mean the first standalone lemma from this lemma prime, you only have to assume that the first 2 outcomes do not happen. And so automatically, the first 2 outcomes of this lemma prime will not happen. And so you can get a sparse pair of good size, and then you can keep applying lemma prime inside B every time, I think for 1 over Y times to get the third outcome. Okay. And here note that every time you apply lemma prime inside B, the maximum degree condition is still preserved, because in this original lemma, the mass degree of F was Y squared times F. Okay. Right. So let me do a proof by picture of this standalone lemma prime. Okay. So let me assume that the last 2 outcomes don't hold, and then I will try to deduce the first outcome. Okay. So since the second outcome doesn't hold, you can always find a good number of induced copies of H minus U and V, which can be extended in a good number of ways into an induced copy of H minus V in F. So let me pick such an instance. And this brown ellipse is a copy of H minus U and V, and it can be extended to this many choices of U. Okay. So this blue rectangle is the set of choices of U. And I know it is at least this quantity, but I can also pick a subset of it. And let me say A is a set of choices of U corresponding to this brown ellipse and of size exactly Y to the A plus 1 times F rounded down. Okay. Then Now I'm gonna let this ring rectangle to be the set of vertices in the rest of the graph with a neighbor in this blue ellipse. And since f has mass degree at most y times f, the size of this ring rectangle is going to be at most h minus 2 times y times f. And this near wide rectangle is the rest of the graph, excluding the blue rectangle, the brown ellipse, and the green rectangle. So in this near wide rectangle, I'm going to split into two. The red rectangle is going to be the set of vertices seeing at least an expression of A. And I will call the rest, this Y rectangle, to be B. And so B is going to be the set which is expressed to A. And since the third outcome doesn't hold, I'll deduce that the size of B has to be at most 1 minus h times y times f. And so by some calculation, I can deduce that the size of the red rectangle is going to be at least y times f. And since every vertex of the red rectangle can be chosen to be a candidate for V, I can actually form many induced copies of H by combining the brown ellipse, some vertex in the red rectangle, and its neighbors in the blue rectangle. And that's the proof by picture. Any questions? Right, so let me conclude the talk by talking a little bit about ordered graphs and tournaments. So Alan Park and Solimushi in 2001 also proved that the Erdős conjecture for graphs is equivalent to the ordered graphs version and the tournaments version. And actually, the proof method that I have introduced also works well in the ordered graphs and the tournament setting. So let me define the family fancy K of ordered graphs. Every induced ordered subgraph of K in the family either can be obtained by interval substitutions or has a vertex of degree 1 on the far left or far right. And our result says and our results, yes, so sorry, it is a little bit so not every K in fancy K, sorry, but every K such that both K and its complement in fancy K has the Erdős property. And from the, okay, so this result actually says for every K and K prime in fancy K, the pair K and K prime complement has the Erdős property. Sorry about that. And from this result, we have some corollaries, that is excluding monotone paths and antipaths by Park and Tolman, and new ordered graphs with the Erdős property and new tournaments with the Erdős property. Yeah, so that's the end of my talk. Thank you.
Okay, on the count of 3, let's all unmute and give Tung a round of applause. 1, 2, 3. Okay, are there any questions? Do you think it should be true that the Erdős property implies the viral property?
Yeah, good question. So so let me go back to where is it? Yeah, the fact that all graphs known to have the Erdős channel property are also viral. This includes C5. And actually, to prove that C5 is viral, we actually got that from the Erdős channel property of C5. So there is a step in the proof where we use the Erdős channel property of C5. And yeah, I guess there might be a way to show that the Erdős channel property implies the viral property, but I don't know.
Any other questions? Okay, well, thanks, Tung, for a great talk. I'll stop the recording and we can continue discussion off the air.